This is AP Calculus AB B, Unit 3, Lesson 2, Slope Fields, the unit being differential equations and mathematical modeling. The idea of solving a differential equation by taking the antiderivative is pretty foundational, and it works if you can solve for the antiderivative. Now, when there is an x and a y as part of the function, then taking the antiderivative is not so easy because y being a function of x, we would need some sort of counter for the chain rule, all right, working backwards, and that can become really complex. So these are not easy to integrate, but one of the things we will note is that when you do integrate, you remember we add the factor c, and so we create a whole class of functions given different values of c. And so one of the useful things in differential equations is to create what's known as a slope field. And to create a slope field, you need to be able to solve the differential equation for dy dx, or the rate of change of the independent variable, in terms of x and y. And I've got an example up here on the screen. And let's go ahead and see if we can generate by hand the slope field. Slope field basically says we're going to take a graph, a Cartesian coordinate system, and we're going to apply the x and y values at each of the points on the grid to calculate the slope being the rate of change of y with respect to x. So here we go. We have the point 0, 0, right? dy dx of 0, 0 is 2 times 0 plus or minus 0, which is 0. So this has a slope of 0. So what we do is we put a dot here and a little line indicating a slope of 0, a horizontal line. Okay? All right, and then we do the same thing for dy dx for, let's say, 1, 0. 2 times 1 is 1. Minus 0 is 1. So over here the slope is 1. That's a perfect 45-degree angle. Okay, I'm going to work more in my head now. So 2, 0, that's 4, 0. So that has a slope of 4. So quite a bit steeper. 3, 0. 2 times 3 is 6. Minus 0 is 6. So a little steeper. So as we move to the right, it's getting steeper. As we move to the left, negative 1. 2 times negative 1 is negative 4. Minus 0 is negative 4. So it's pretty steep, but negative. Okay. Then plugging in negative 2, 0. 2 times negative 2 is negative 4. Actually, I goofed on that last one, didn't I? 2 times negative 1 is negative 2. Minus 0, so this just has a slope of negative 2, so it's kind of like that. Okay, and this one has a slope of negative 4. And 2 times negative 3 is negative 6, minus 0 is negative 6. Okay, let's do a few more points. I may or may not do all of these. Okay, let's try 1, 1. 2 times 1 is 2, minus 1 is 1, that has a slope of 1. Okay, and I think if I go here, let's go here. 1, 2, that's that point. 2 times 1 is 2. 2 minus 2 is 0. That has a slope of 0. Okay. And 1, 3. 1, 3. 2 times 1 is 2 minus 3. That has a slope of negative 1. Okay. And let's go ahead and do some more. 2, 2, 4 minus 2 is 2. 2, 1, 2 times 2 is 4, minus 1 is 3. And 3, 1, 2 times 3 is 6, minus 1 is 5. That's pretty steep. And 3, 2, 2 times 3 is 6, minus 2 is 4. And And 3, 3. 2 times 3 is 6, minus 3 is 3. Okay. 2, 3. 2 times 2 is 4, minus 3 is 1. Okay. And let's do some of these here. 2 times this point is 0, 1. 2 times 0 is 0, minus 1 is negative 1. 0, 2. 2 times 0 is 0, minus negative 2. Actually, minus 2, minus 2. This is negative 2. 0, 3. 2 times 0 is 0, minus 3, so it's negative 3. Okay, and so on and so forth. Okay, I'm going to go ahead and stop here because I think you get the idea. So you plug in the x and y values, calculate the slope, and then sketch a little segment of a line that demonstrates what that slope looks like. Just to remind you again what slope looks like. A slope of 0 is flat. A vertical is undefined, and so it's not going to occur. But a slope of 1 is a perfect diagonal. A slope of 2 is a rise of 2 and a run of 1, so it looks like this. So it would look like that. A slope of 3 is a rise of 3 and a run of 1, so it would look like that, and so forth and so on. And you kind of get the idea. Think in terms of rise over run. Okay, that said, if you Google slope fields, you can come up with several Desmos and slope fields. You can come up with several Desmos pre-made deals that have these, and you can put in any formula you want. You can do x over 2y, right? And we can get a graph from that, and this is a slope field. Now in this case, we can put in the slope field for the formula we've got, which is 2x minus y, 2x minus y. Okay, and there it is. There's kind of what I was getting at here. We got kind of the top right corner here down by 3, negative 3. So it goes out to about here, 3, negative 3. So we've got these slopes here that we were finding. And that seems to be what we are finding. Now it's interesting, this particular one has a movable field. It's kind of like a magnet. You can move it anywhere and it'll give you the slope at that point. And as I move across here, something happens drastic. It's got 0 slope right there, and then it goes there, and then it starts to move slowly, right? So it flips around, and same thing going top to bottom. Okay? Now, we can find specific values, and I'm not going to get into the mathematics of it. This is a linear differential equation, and there's a technique for solving linear equations that we're not going to learn in this course. You take your Intro to Differential Equations course to do that. But the general solution is y equals 2x minus 2 plus some constant. There's that constant that we put in. I'm going to call that a1, e to the negative x. Okay, and I'm going to add a slider for a1. Okay, and this represents a whole class of functions that fit this slope field. So you can use a slope field. Using a slope field, you can kind of sketch specific solutions given one of the points. Okay. So as I change the value of the constant, you can see the function itself moves around. And ultimately would cover all of the possible solutions. Okay, let me hide this here. Let me screenshot this and just show you very quickly here how we can sketch a specific solution from the slope field. Okay. So let's say I pick some random point on the graph, maybe even where the magnet is right now. Okay, and I can sketch. Let's use green. I can sketch the slope right there and just kind of picture trend lines. Right here, here it's 0 right here, and it seems to go up like that and focus like that. Okay, and so just kind of going in the direction the slopes indicate. Right, and that would represent a specific solution. If I start somewhere else, I can get a totally different result. If I start, say, right here, I can follow the directions, and this is generalizing, of course, and we can get another specific solution. Okay, so the slope field is kind of like viewing vector currents or water currents in a fluid. Really kind of fascinating. All right, so hopefully that makes sense.